All right, folks, this is a much shorter video on the total mechanical energy of planets and something called escape velocity. So you will escape this play closet, I promise, and you won't have to run at 100 miles an hour. All right, so quick review of total mechanical energy. Just like we did for things like in the lab, objects, small objects, the total mechanical energy is going to be all the stored energy and all the kinetic energy. All right, so in general, there's a lot more terms to TME, but the only type of stored energy we're going to count is the gravitational stored energy. And one of the biggest things that's easy to get wrong, I got some warnings coming up, but do note that minus sign. That's not, like, make sure you put that in your notes. That's not part of the fraction. So this is what I derived in the last play posit. Please make sure you listen to that one first. Plus the tangential velocity. All right, we're only going to count 1/2 mv squared if there's a planet that is also rotating and revolving around the sun. We're not, or if the satellite is rotating, we're not going to add 1/2 I omega squared because that rotational velocity, kinetic energy, tends to be constant. All right, so we're not counting any chemical energy stored in, the batteries on board. It's always just going to be these two terms. Okay, so that's the good news. Okay, heads up. Really easy. I do it all the time. These two equations are so similar. Don't go on autopilot and you do r squared. All right, so you get these two formulas on the formula sheet so you can quickly check your work, but the force of gravity is positive and is over r squared, and the stored energy is negative and it's just over r. So be super careful. That's real easy to confuse. All right, and then second heads up, you got to put that minus sign in there. That is not optional. That's part of the definition, that it's got to be in there. All right, quick review question. Where is sea level for planets when we're talking about the real UG? Okay, awesome. Sea level is at infinity, but not beyond. All right, somewhat of a review. What do you think it means if you calculate the TME of a satellite using the two terms we just talked about and you get a negative number? What do you think it means that if the TME is negative? And sorry, I can't remember if the answer's on the next slide. Yeah. Okay. The reason I ask you where's infinity, where is sea level, and what does it mean if you have a negative number, is to give you a heads up for this slide. So something that I think will make more sense, a little bit more concrete. You have a bucket of water and it is below sea level. All right, so if you calculated your MGH, you would have a negative number, let's say minus 30 joules. What does it mean that that bucket of water has negative 30 joules of total mechanical energy? It means that in order to get to sea level, where I have no stored energy, I've got to put 30 joules in just to get to the point where I'm at sea level. Okay, so it's kind of like if your net worth is minus $30, you've got to pay your friend the $30 back before you have a net worth of 0. So like you're in debt. Okay, so the negative is not a problem. It just means in order to get to sea level, I got to put some energy into the system. All right, so which of these, oh, sorry, let me tell you a little bit, give you some background. So this is a depiction of something that I think it's Newton, not Galileo, that Newton put in one of his notebooks. And so he imagined, this is so not to scale, but he imagined throwing a rock off of a really tall mountain tangentially. So perpendicular, like totally perpendicular to the radius. And first you have projectiles, like we did in the first play posit. These are parabolas, so bigger and bigger, bigger parabolas. So A and B are parabolas. C is the, if you remember, it's been a while, but remember there was one perfect velocity. One perfect velocity, so that if you threw it at this radius, the attraction to the Earth was exactly what it needed to be to just turn the object. If you didn't give it enough velocity, it overturned and became a projectile. If you give it too much velocity, the Earth doesn't pull it back soon enough, and it becomes an elliptical orbit. And if you give it even more velocity, it will follow this path. Okay, and this is where we're eventually heading. This escape path means it's going to go farther and farther and farther out. It is going to slow down, but the pull from the Earth gets weaker and weaker and weaker and weaker, and so it makes it out to infinity and never returns. Okay, so my question to you is, which, if any of these paths, have a negative total mechanical energy? Okay, the correct answer is A, B, C, and D, because none of these are ever going to make it out to sea level, which is an infinity. E will just make it out there and like crash at the finish line with no kinetic energy. And if you launched it with yet a speed a little bit more than E, it would make it out to infinity with some speed. Okay, so please write this down. Definition of the escape velocity of an object is what people mean when they say that. It's the speed that a satellite or an object must have at whatever point you're talking about in order to, so the speed that you must have at point A in order to reach infinity, which is going to be point B, and just barely make it there with zero speed left. All right, so that's like saying a roller coaster just gets up over this hill and then falls back down. Okay, so it just makes it to the top of the hill with zero speed. Okay, so just for a quick visual and a reminder of, pretend like that total energy line is not there. So if you, and pretend like this is the Earth, if you throw something up, so if you throw a ball up with one speed, it'll come back down. A little bit faster, it'll go higher, and it'll come back down. Yet faster still, it'll come back down. However, since the real force of gravity decreases with distance, as you go higher and higher up, it's going to slow down at a decreasing rate. Okay, so let's say you throw something up on the surface of the planet, and this is a picture on the left here. This is a picture of, the actual distance, where this is the, these are the different max heights. Okay, this, I don't want to confuse you. On this picture, this graph is the total energy. So this is the distance running horizontally, and that's the energy. Okay, so you start at the radius of the planet. You can't, that's your initial, that's your point A. Okay, let's say that so even at point A, you are in the hole gravitationally. You've got negative stored energy, right? You're in the fourth quadrant. So let's say you give it some amount of kinetic energy here, so that this is your TME. So let's just, to make sure that this potential energy graph makes sense, at point A, you have a bunch of kinetic energy. Remember, that's the difference between the total mechanical energy and the stored energy. So you got this big green line represents your kinetic energy. As you move away from the planet, you're gaining stored energy because it's becoming less negative, and this pink line is less than the green line because you have reduced your kinetic energy. And then you keep going, and you have your stored energy is less negative, right? You used to be way in the hole here, so you have more stored energy, and that it's less negative, but your TME is going down. And your TME gets even smaller and smaller and smaller, and at some point, remember where the TME line, did I say TME? Your kinetic energy is going down. And where the TME equals the kinetic energy, that's what's happening here. Sorry, when your TME equals your stored energy, because your kinetic energy is going down, when your TME equals your stored energy, at that point, you have no energy left over to be kinetic. So this is where your kinetic energy is 0, and that's your turnaround, and you will fall back down to the planet faster and faster and faster. Okay, so hopefully that made sense. So what we are trying to do is say there's some value of kinetic energy, this green line, such that it will decrease, and it will decrease, and it will decrease as R increases, meaning I'm getting farther away from the planet, and it gets smaller and smaller and smaller, but at a decreasing rate. So that at some point, it's possible that I just make it out to infinity because of those crazy things of limits. So I lose more and more and more and more kinetic energy, but I have enough so that, it's one of those infinity things. I do make it out to infinity and I just barely lose all my kinetic energy by the time I get out to infinity. Okay. All right, so that was kind of abstract, but we'll do some practice problems, not in the PlayPosit. I'll post some. I don't think they've ever purely tested this, but I think I think it's important. I think it'll help give you a visual and some anchor for this information. You should absolutely know that there's only one for any given radius. Remember we talked about geosynchronous orbits? For any given radius, there's only one speed for that radius that will be a circular orbit. Now you could have another radius and a different circular orbit. Okay, so I don't want you to think that there's only one possible circle. That's for this given radius. See, all these curves line up with this radius. So there's only one speed that will give you a circular orbit. We did a PlayPosit on that. It's a good review of circular motion and the real force of gravity. Okay, if you go more slowly than that, you get this blue ellipse that's inside the red circle because you're more bound to the planet because you have less energy. If you go faster than that, at first you get this green ellipse because you're starting to break away from the planet, but it's still less than the escape velocity. What's kind of cool is that if you hit the escape velocity, where you just make it out to infinity with no energy left over, it's a parabola. And then if you throw your physics textbook because you're done with physics at the end of the year. With a speed faster than that, you get any number of hyperbolas and you make it out to infinity with energy left over. Okay, so that would be like the difference between pulling that bucket of water out of the well and it's at rest when you take it out, or when you pull it out of the well if it actually has some velocity. All right, so just super quickly for some reference, so it hopefully has some more meaning. You can calculate the escape velocity at the surface of each planet. If you already had some height because you were a satellite, you wouldn't need to have quite as much speed because you've already pulled yourself a little bit away from the planet. So this is the Earth's escape velocity in kilometers per second. So if you want that physics textbook to never come back, you're going to have to launch it at 11 kilometers per second. Pretty dang fast. And the only other thing I want to say about this is this escape velocity will determine partly and temperature how much atmosphere a planet has, because the higher the escape velocity, the faster the molecules, like oxygen, let's say, which we want to have around our planet so we can breathe. In order for an oxygen molecule to escape the Earth and not be part of our atmosphere anymore, it's got to be going that fast. Okay, so that's, and the speed of the gas has to do with the temperature, et cetera, et cetera. So that's why the moon has very little atmosphere, is because it's not on here, but the escape velocity of the moon is not as big. And so if the molecules in the air have enough speed, they're going to escape. All right, I think we got 3 more slides. All right, so to calculate the escape velocity, it is not hard. Please do the posted AP review problem so you just get comfortable with the R and the minus sign and nice review of energy, so that if you get a planet problem on the AP, you kick butt. Okay, so we're assuming that there's no energy loss to air resistance, which again, in the real world, if you're launching a satellite, that's not true. But so we're going to say that energy at the surface, or some other point if it's already in orbit, equals the energy at infinity, because that's what it means to escape. We got to get to infinity to fully escape the planet. So what kind of energy do I have? Our new UG term, don't forget the minus sign, don't forget R isn't squared, plus some regular old school kinetic energy. Then I'm going to go out to infinity. Remember, if R is infinity, this approaches 0, so awesome. That term goes away. To just escape, I don't want to have any energy left over, so I'm going to set the kinetic energy equal to 0 as well. Okay. Be careful. There's 2 M's here. It's the mass of the satellite that cancels, not the mass of the planet is still in there. That's why in that chart, each of those planets had a different escape velocity. It is a function of the planet. It is not a function of what the mass of your physics textbook, because we're calculating the escape velocity. So all molecules have the same escape velocity. They have different energy. So if I said how many joules of energy do I need to give, clearly I don't need to give my physics textbook as much energy as I would need to give the space shuttle. Okay, so it's not a measure of the energy you need. The more mass something has, the more energy you will need. But they all need the same speed to escape, right? Everything falls at the same rate. The bowling ball and the feather, even though they have different amounts of energy. Okay, so as you can see, not super hard conserving energy. You guys are good at that. I will give you a quick warning on the next slide. I'm not good at memorizing. Be careful. If this is on the multiple choice, by all means, it will help to have memorized this. But if you go back and look at your notes for the speed of a planet going in a speed of a satellite going in a circle of radius r, it's super similar. There's no 2 in it. So this was the speed for circular motion for a given planet at a set radius. Okay, and this is the formula for escape, which what I think is kind of cool, and I'll try not to geek out, so they'll keep this shortish, is for Newton on that impossibly tall mountain, if he wanted to throw something so that it went in a perfect circle, it would be this speed. If he wanted to increase the speed so that it never came back, it only needs to be square root of 2, or 1.41 times the speed to go in a circle to never come back. What? And I think that's just a function of the fact that gravity decreases with distance. Not sure, but anyway, that's why just be really careful if you go on autopilot. If you're doing the multiple choice and you plug and chug into these formulas, please make sure that you know which formula you're using, because for sure they're probably going to have that quote wrong answer, right? So escape velocity has the extra 2 in it. The speed to go in a specific circle does not. Okay, if the planet problem is one of the 3 free response questions, definitely don't just slap that formula down, because you know that the rubric for the points, you get a free point for saying TME equals TME, free point. TME for understanding that there's no kinetic energy at infinity. Like, there's all kinds of points here, and if you just plop this down, you're going to get nothing. So show the work. This is not a hard proof. Okay. The last thing we're going to do is the other type of problem, and I'll post these for you guys to practice, is they might say there's a satellite in a circular orbit and we want to change it to an elliptical orbit, or we want it to go out to infinity or something. They'll say, how much work do the jets of the shuttle have to do in order to do this? All right, so this is just connecting techniques that you've already used with the new formula for gravitational stored energy. So you're going to say I have the TME at A, and you might have already done a problem where you found the speed because you're going in a circular orbit. So plug and chug into your formula for UGA. Don't forget that it's R and the negative sign, plus the speed that either they give you or that you find from doing circular motion, plus work, equals whatever UG at B is. So if the radius is the same, then that might even be the same term. If the radius is bigger, if you're going to move it into a bigger circular orbit, then just read the problem, plus the kinetic energy at B. So plug and chug, solve for W. And then final, this is the final slide. Don't freak out if you get 10 to the, 6 joules. A joule is a tiny unit for engineers, and it's even tinier if you're talking about massive spaceships, shuttles or whatever. So don't freak out if you get tons of joules. We're not dropping, ping pong balls in the physics lab. Okay? So the point of this play posit was just confirming that most of the time your TME for satellites will be negative. Don't freak out if you calculate the TME and it's negative. It just means that you're in an orbit. Okay, if you know the planet's in an orbit, you better get a negative. And then you can conserve energy from one point to another, just like we've done before. And you can also say that energy isn't conserved because there was air resistance or you turned on some jets. All right, I'll give you some practice problems. That's the best way to understand this. And thanks for listening.